Hello, AutoML 2022. I'm Leonard Puroka and I welcome you to this presentation of the workshop paper Assembled-OpenML, creating efficient benchmarks for ensembles in AutoML with OpenML. Let's jump right into it. The idea of assembling is to aggregate the predictions of multiple base models with the aim to achieve better predictions than any individual base model. And in this format, ensembles are often used in AutoML. For example, they are used as part of the search space. For example, random forest, ADA boost, or gradient boosting are often used in the search space. Or they are used as a special part of the search space. Here, a famous example is stacking, implemented in AutoGluon, AutoStacker, or automatic Frankensteining. Lastly, we can also assemble post-hoc after model selection. Here, examples are greedy ensemble selection or automatic dynamic ensemble selection, where the idea is to find the best ensemble for all models found during model selection. And if we were now to benchmark ensembles in AutoML, this is a bit more tricky for the last two parts. For the first part, it's almost identical to benchmarking normal algorithms. However, for the second and third part, for a special part of the search space or for post-hoc after model selection, it becomes much more expensive and harder as a result of AutoML. Usually, benchmarking ensembles is expensive because we need to costly train and evaluate many base models on many datasets, to then later evaluate the performance of our ensemble methods. However, this is even more expensive for AutoML because of two reasons. The first one being we require authentic base models, that is, models from model selection. In other words, for a dataset, we need to employ model selection to find the many base models which we want to train and evaluate. And as you may know, model selection is very expensive. The second reason is that we assemble many different types of base models that can be very expensive to train. For example, usually in random forest, we assemble many small trees. But here in our AutoML use case, we want to build ensembles of ensembles, or in other words, ensembles of very expensive base models. As a result, the overall process is much more expensive. And we plan to make this more efficient with OpenML. OpenML is an online platform that stores data on machine learning experiments. And specifically, OpenML stores the out-of-fold predictions of evaluated models. We can fetch the out-of-fold predictions, for example, the top 50 evaluated models, and store them in a metadata set. Afterwards, we can use the metadata set to simulate ensembles and benchmark their performance. This process has multiple advantages. First, getting the data from OpenML is like an efficient alternative to model selection. And it is, to some extent, model selection, because we can filter the evaluated models for a given metric. Second, the metadata set is easily shareable and recreatable and functions almost like a tabular dataset or a lookup table. Lastly, the simulation is very efficient because of the lookup table. It is reduced to almost only the computational cost of the ensemble method itself. And in our paper, we have proposed and implemented Assembled-OpenML, a tool for the first two steps. And in future and current work, we want to extend the framework to also include the later two steps. To conclude this presentation, we want to quickly talk about example results before we say goodbye. We used Assembled-OpenML to gather the predictions of 1,500 base models over 31 datasets, and this took 1 hour without parallelization. For comparison, we gathered the prediction of one base model for one dataset without Assembled-OpenML, and this already took 37 minutes with parallelization on 64 cores. In other words, using Assembled-OpenML is much more efficient than doing it the old way. For more details and insights, feel free to read our paper or meet me at the conference in person. Thank you and goodbye.